What up, calculus students? Let's do 9-1 homework on approximating areas using geometric figures, what's called Riemann sums. These are just formulaic ways to approximate area. If you have limited data, maybe you can't take an antiderivative, you don't have a calculator. Now, we could do our calculations with a calculator, but be okay with like writing out what your Riemann sum would equal and not worrying about all of the arithmetic that goes in. I'll show you what that means. All right, so we have a velocity of some particle. We have certain velocities over certain time intervals. I'm assuming it's like meters and seconds. We're approximating the integral from 0 to 8. And what would these approximations represent in the real world? So it's important. We're pretty much reviewing Unit 7 and Unit 8. So remember, velocity values are derivatives. Velocity being positive, being negative, tells us about our position increasing and decreasing. Remember that the area, the accumulation of velocity, is how much our position increases or how much our position decreases, or it's the displacement. So it's the displacement of this object, this particle, from 0 to 8 seconds. So it's going to incorporate the negatives and the positives, add them all together to figure out how far you ended from how far you started. It's like x of 0, wherever that is. Maybe it's c, I don't exactly know, versus x of 8 is equal to some number plus c. And the difference is the displacement. So how do we do this? Well, we imagine that this is on a graph where we have, a base of a rectangle. And then we choose different heights of our rectangles for our left Riemann sum and our right Riemann sum. This is a base of 2. I'm going to use a height of -2 for this first interval. This is a base of 1. I'm going to use a height of 0. This is a base of 2. I'm going to use a height of 3 on the left. This is a base of 3. I'm going to use a height of 7. So if this was like a free response question and you didn't have a calculator, you'd say the left Riemann sum, the integral from 0 to 8 of v of t dt, is approximately 2 times -2 plus 1 times 0 plus 2 times 3 plus 3 times 7. Okay? And if you want to find the value, you could do it. -4, 6, and 21. 23. The right Riemann sum does the same thing, only uses the heights on the right of all of our intervals. So the right Riemann sum approximately would be 2 times 0 plus 1 times 3 plus 2 times 7 plus 3 times 12. 12, 24, 36, 50, 53. And if you have your calculator, it's like, just go ahead and use it. What? Oh, yeah, I got it. Trapezoids are interesting. The trapezoids that we are going to be dealing with look like the trapezoids that you're not maybe used to, but you saw last unit, where we're talking about a triangle on top of a rectangle. Now, the area of a trapezoid is 1/2 the height times the sum of the bases. When we turn it on its side like this, you can see the height is just x distance. This base length would be a y length, and the other base length is another y length. So what we do is actually use both of the y values, -2 and 0, 0 and 3, 3 and 7, 7 and 12. And we just make sure that we have the 1/2 delta x, sum of the heights. Hold on a second. All right, and then like I'm not going to type that into my calculator, but you could. And if it's free response, you don't have to type that into your calculator. All right. Given velocity is derivative is positive, and its second derivative is positive. Like, what is that? What? If velocity, its sign is of the derivative is positive, velocity is increasing. If velocity's second derivative is positive, then velocity's derivative is increasing, or the velocity is concave up. This is very important. If you have a graph of v that is increasing concave up, which approximations are over or under, and why? The left Riemann sum is going to be under. It kind of makes sense. You get the smaller value versus this. Why? If you're talking about using your left y's on an interval where your y values are increasing, the left y's are the lowest y value if your function's increasing. So this is definitely under. Why? Because velocity is increasing. Versus a right Riemann sum was using the y's on the right, it would be an over approximation. Why? Because the velocity is increasing. It's not because of the concavity. It has nothing to do with concavity. Versus a trapezoidal Riemann sum, if you're talking about something curving upward and you're connecting two y coordinates with a straight line and using both of the y values and using a triangle on top of a rectangle, you see that since you're concave up, we are going to be over, we have more than what we're looking for. So it's over because v is concave up and increasing. What would be an approximation for a of 4? Okay, so we got to remember that acceleration is just a derivative of velocity, which means it's a slope of velocity. Well, like, how can I find the slope of velocity if I'm given just some points on velocity? This is important. We're just going to do the best we can finding a slope with the information that we have. We're going to go back to using the slope formula. 4 is smack dab between 3 and 5. Let's find the slope of v from 3 to 5. And it's just y2 minus y1 over x2 minus x1, 7 minus 3 over 5 minus 3. v2 minus v1 over t2 minus t1. So it'd be 2 meters per second squared. You guys really struggled on rates of change and their units. Acceleration's units are like meters per second squared. Using a right Riemann sum, calculate this. Now, you got to be comfortable seeing this and understanding that you could rewrite it like that. Like 1/8 times an integral is the same as an integral divided by 8. You should be familiar with this, where it's like, oh, we're adding up, we're summing up, we're accumulating all my velocities, and then we're dividing it by the interval. This is the average velocity. It's not an average rate of change of velocity, it's an average rate of change of position. It's an average velocity. I got my right Riemann sum as 53, and I divide that by 8. What if I'm talking about the absolute value of velocity? Well, this is when we're like accumulating all of our positive displacements. This is when I'm accumulating my speed. What is this? This is going to be a total distance that the particle traveled from 0 to 8. All that matters for a right Riemann sum is making sure all of your y's are positive. It's not going to change anything. It's still going to be 53. If I used a left Riemann sum, which would probably be better, I would change this -2 and make it a +2. I would not say that this is a displacement of -4. I'd say this is a distance of +4. So let me just change it to left Riemann sum, just so you know the difference. the left Riemann sum is going to be 2 times positive 2. So we're going to use the positive velocities. 1 times 0, 2 times 3, 3 times 7. Okay, and that's if you use a left Riemann sum. All right, this next question is great. What would be the value of the integral from 0 to 8 of a? Well, like the integrals of a, the accumulations of a are going to tell you how much v increases or decreases. If you remember your second derivative sign analysis, v prime will tell us about v. The accumulation of v prime will tell us how much v is changing. That's one way to think about things. And how do you find this value? Well, you could take your v at a value and subtract a v at a previous value. Subtract these two things, boom, you get the distance, or you get the displacement of velocity. Or don't forget, and it's something that we haven't really seen / done much because we've been able to use your calculator, that if you ever have an accumulation that you want to find and you don't have a calculator, you can always think about taking the antiderivative. The antiderivative of a is v. Cool. Maybe you have a plus c. Who cares? It won't matter. Now I'm going to use this line to denote I've taken the antiderivative, but I still need to plug in 8 and 0. Now this line represents find the change or find the displacement of your velocity. Many times we kind of go straight to the calculation of v of 8 minus v of 0. V of 8 minus v of 0 is how much v changed, which will be the accumulation of v prime. Newton antiderivatives to find accumulations. You can go back to your table to find v of 8, which is 12, and v of 0, which is negative 2. You get ended at a velocity of 12, started at a velocity of negative 2. The displacement of velocity was 14. That'll be the area under acceleration. Now here, the second one, this is the change or displacement of velocity from 0 to 8. Now here, we are trying to find the accumulation of acceleration and divide it by 3. We should be familiar with this as being like, oh, an average acceleration from 2 to 5. Now, this is where we go back to average rates of change of v. The rate of change of v is a, so this is just an average a. If you find the average rate of change of v, you'll find an average a. Maybe that makes sense to you. Don't worry about it if it doesn't. If you don't have information to provide to get this, if you can't plug this into your calculator, if you don't have a calculator, look to take the antiderivative and find the displacement of velocity. This is going to be the average rate of change of velocity, and a rate of change of velocity is an acceleration. So this is an average acceleration. V of 5 is 7, V of 2 is 0. So this is 7/3. And that's the average acceleration from 2 to 5. Okay, this is us reviewing Unit 7. Motion. Only we can't find exact positions, exact anythings. And now we come to this question, and this is like our Unit 8 rate problem. But I have some a table of information. Now let's read the question, make sure we understand what's going on. We have water being pumped into a tank at a rate modeled by W. All right, so this is our rate in liters per hour. Remember, it goes position, velocity, acceleration, F, F prime, F double prime, position, position's derivative, position's second derivative. We are given Liters per hour. Liters per hour would fall here in the velocity, in the derivative category. Liters per hour squared would be an acceleration, it'd be the derivative. If we want to find a position, we would need to accumulate. R is the rate out. So this is my rate in, this is my rate out. We have an initial amount of water in the tank. R is decreasing. That's important. Approximate R prime of 2. Explain, using units, explain the meaning of your value. Many of you messed up on this on the test. When I asked you what is the rate of change of the rate at which things were changing, R prime would be the slope of R. At 2, the best thing I could do is using the slope between 1 and 3. Now, what's the top values? Liters per hour. What's the bottom values? Hours. What are you doing? You're given a derivative, you're given a velocity. You take the derivative, this is going to be like an acceleration. I'm not going to say my acceleration's this. Rather, my calculations of the slope of this rate of change would be a second rate of change. Negative 120, it's not liters per hour, it's liters per hour squared. It's an acceleration. It's a rate of change of a rate of change. So we would say R is decreasing at 120 liters per hour, or liters per hour squared. Approximate the integral from 0 to 8 using a left Riemann sum. Using correct units, what is the meaning of your answer? Is your approximation over or under the actual justifying answer? All right. Left Riemann sum, approximate the accumulation of R. Here we go. 0 to 1, the base length is 1. I'm going to use 1340. 1 to 3, the base length is 2. I'm going to use 1190. 3 to 6, the base length is 3. I'm going to use 950. 6 to 8, the base length is 2. I'm going to use 740. I'm not going to do the calculations. We're going to pretend this is free response, no calculator. And you're okay with just writing this out and being like, free response, our answers don't need to be simplified. Cool. Whatever that is, that's what it is. Now, what does it represent? Well, I'm accumulating my rate out. This is going to be my total out, the total water removed. What is the units? Well, it's like, what are you doing? You're taking an hour and multiplying it by a liter per hour. You're taking your liters per hour and multiplying them over a course of hours. Liters per hour times an interval of hours will give you liters. We accumulated a velocity to get a displacement of position. We went backwards with our derivative sign analysis. This function's decreasing. I'm using the larger y's on all of these intervals. Since I'm using the larger y's, this is an over approximation. You can draw a graph if you want to, if something's decreasing and you're using the y value on the left over that interval, then we can see we are over approximation. What is the reasoning behind it? You were told R is decreasing. Done. What is the rate that the water level is changing at t equals 3? Is the water level increasing or decreasing? This is when we think about all of the factors in play. Let's start with our position. Well, the position is going to be 50,000 plus however much came in minus however much went out. which means the derivative. Many people were not writing P prime on their test, which means you really don't know what you're doing. You're just trying to memorize processes versus like understanding. We evaluate derivatives to understand how original things are changing. The derivative of this is rate in minus rate out. Okay? P prime at 3 will tell us whatever this value is, whether it's positive or negative, will tell us how P is changing, how quickly P is increasing or decreasing. A rate of change will tell you how an original thing is increasing or decreasing. So I need to find W of 3 minus R of 3. Now this is when maybe you are using your calculator and you need to find W of 3. There's two ways to find W of 3. You guys should be used to it. One could be just plugging in 3 into W. Cool. Another way to be graphing W. Now this is not helpful as we do not have something to graph R for, but if you want to graph W, maybe to accumulate it later so that you can use Y1 more often. This is just W, this is just the rate in, this is just how quickly things are coming in. And then I have a boatload of quizzes.
Definitely my work on the other one here, but so yeah. He said that. He said that like he didn't know the period of this was, and the period of some of this. He was like, I said, period 6, period 3, period 6, and so he was still like.
Yeah, 3.
Okay. I think he like said the periods were like half of that, and he like didn't know for sure, or whatever. But I didn't want to tell him that. So.
Did you share it with me?
I'll send it to you right now. Cool. But again, like it's not great, but
I'm sure it's fine. I'm just in calculus land these days. Yeah. If you plug in 3, boom, there's W3. You could also do W of 1 of 3 this way. This actually plugs in 3 into W of 1. It's kind of crazy how it does like that. Okay, cool. So that's W3, 1275 liters per hour minus R of 3. What the heck is R of 3? Well, here's R of 3, 950. And you get this, 325.256. This is liters per hour minus liters per hour. This is liters per hour. It's not liters. These are velocities. So what is this telling you? P, the total amount of water in the tank. Is it another water in the tank question? Yeah, another water in the tank question. Water in the tank is increasing by 325.256 liters per hour at t equals 3. A derivative, instantaneous rate of change. Okay, using a trapezoidal Riemann sum with sum of intervals indicated by the data and the other information provided, approximate the total water in the tank at time 8. If R of t was decreasing at an increasing rate, it's not, but pretend it's your approximation over or under. Okay, so we're trying to find the total amount of water in the tank at time 8. We had an initial amount. We need to accumulate our rate in to get a total in. we need to subtract accumulation of our rate out, which will be a total out. This is where having W graphed is helpful because you can just go 0 to 8 of W. You need dx. Okay, is it 50,000 or 5,000? 50,000. Okay, so I got 50,000. I add this much. Now, how much am I subtracting? Well, I got to use a Riemann sum to get this. Let me just zoom out a little bit so I can write it out. Okay, the trapezoidal Riemann sum uses both y values. That one and that one, that one and that one, that one and that one, that one and that one. So let's just write it out and I'll actually do the calculation. 1/2, 1340 plus 1190. Oh gosh, there's too many parentheses. 1/2, 2, 1190, 950. That's right. 1/2, 3, 950, 740. 1/2, 2, 740, 700. Now let's just do this in the calculator. I'm gonna factor out all the 1/2s just so I don't have to do it. I'm just gonna do 1 times the sum. Okay, 7380. I have 50,000 to start. I added 7,836. I lost approximately 7,380. I have a total of approximately 50,456 liters. If R is decreasing at an increasing rate. All right, let's talk about this. It's so funny. All my stuff just disappeared. Well, that's what happens. If R is decreasing at an increasing rate, so R is going down, R's rate is going up, which means R double prime is positive, which means R is concave up. If R is going down and concave up, and you're using a trapezoidal Riemann sum, this will be an over approximation. It's an over approximation of how much went out. So if you have 50,000 plus a total amount in, and you subtract more out than you should be, this is an under approximation. Under because my trapezoidal Riemann sum of R is over, and I'm subtracting more. It's a great question. Is there a time when the water level is constant? What time interval? Would that be a location of a max water level or a min water level? Well, it's like we can see W is decreasing. W starts at 2,000. W gets to 81. We're going to cross over somewhere. I don't know exactly the easiest way to do this. I'm going to just kind of put some points down, and I see like my rate in is bigger than my rate out at 1. My rate in is bigger than a rate out at 3. At 6, my rate in is smaller than my rate out. Somewhere between 3 and 6, rate in is bigger than rate out. Like rate in is bigger than rate out at 3, but rate in is smaller than rate out at 6. So somewhere between 3 and 6. Okay. We start with my rate in being bigger than my rate out. So that means my derivative is going to be positive from 0 to that point A. And then my rate out is bigger than my rate in. So my derivative is going to be negative from like A to 8. So if my derivative goes from positive to negative, my amount of water is going to be increasing and decreasing. It's going to be the location for max. All right, we'll finish this during lunch.